So let's get started. Here you see the home page of the Xilinx Power Designer. We have the capability to open a project, to scan and monitor an existing product that has been live that we're using in the lab, for instance, or we can open a new project. Please note that there are several other segments within the configuration browser. We'll be going over some of these a bit later in the demonstration. So let's first click on Loads. Here we have the option to create a new load or import a load from a different data file. There are two types of data files that are supported for import. Xilinx Power Designer exported load files having a .load extension, and Xilinx Power Estimator exported data files with a .xpe extension for the Vertex UltraScale Plus family of products. For this demonstration, we'll be focusing on importing a file from the Xilinx Power Estimator. So let's leave this screen for a moment and let's go to the Xilinx Power Estimator webpage. I want to emphasize that the Xilinx Power Estimator is a Xilinx tool. As I'll be showing you in a moment, we will use the export function within the Xilinx Power Estimator to export a Xilinx product file to the Xilinx Power Designer. So now let's scroll down to the download section. At this time, only the Xilinx Vertex UltraScale Plus family of products is compatible with the Xilinx Power Designer. The further updates will include more FPGA options. So let's select this download link, and we'll be downloading a spreadsheet, which is the Xilinx Power Estimator. Now let's go here under Device to Family, and we want to open up an available section that has Vertex UltraScale Plus products, which will be right there. Okay, it's presently downloading all devices for that family. And now we can select a device we want to work with from that family. Let's select this one. From here, the file can be modified by the user as desired. After modifications have been completed, we then click on the Export File. And then you would save the product name, and we want to save as type to get the proper extension. We need to go with the XPE exchange and save. Remember, the .xpe extension is compatible with the Xilinx Power Designer. After saving the file, we then go back to the Xilinx Power Designer screen. Now we click on Import Load. We then scroll to where we had saved the Xilinx file, and we open this file. Now we see the load inputs that are available for input. Essentially here you can keep or deselect any of these loads as you see fit. And once you're satisfied, in this case, let's keep all 9 of the rail groups, we then select Finish. Now we see this file has been added under the loads portion of the configuration browser. Now let's select this load so we can further examine it. We can see under load inputs that the 9 load groups have been successfully imported. Also below this, for each of these loads, we have more information on each load. It is also possible to import new data to an already imported load by clicking Import Load. Now, I'd like to show you how to use the system optimization function. We first select the system mode, and we click on the Enable System Optimization mode. Now let's select the first load component underneath the image of the Xilinx device. This opens the system optimization screen, and also you'll notice the load group has been darkened after being selected. Let's go over the different tools that are now available to us. The first box, the configured rails, shows a list of a drop-down of all the rails that are going to be optimized. For now, only the first rail is visible, but after all groups have been selected, all will appear in this drop-down. The Remove box will remove the selected rail configuration from the optimization. The Remove All will remove all rail configurations. So be careful before you press this one. Now this slider is used to optimize for maximum system efficiency or for minimizing the overhead of power and current for the power converters. If we move the slide all the way to the right to maximize efficiency, this will select a power converter solution which will yield the highest system efficiency. Moving the slider to the left, we'll select the solution whose load ratings most closely matches the required maximum load of each rail grouping. This will tend to be the lowest price solution and often the solution with the least board area. But keep in mind, the total system efficiency will typically be lower than the solution with the maximum efficiency. Now let's return to the maximum efficiency. Beneath this button, we see the name of the rail group that we're presently working with. It kind of helps you keep things straight. So we can see the VCC-INT, and this is the one that we're now working with. The PCB Output Resistance Box allows the user to set the estimated PCB output resistance for the configured rail between the output of the power module and its loads. The default setting is 1 milliohm. For the VN box, this specifies the bus voltage to be used as the input voltage for all point of loads. The default value is 12 volts, but this field will be read-only if the optimized bus voltage is checked. Here we see a configure IBC. Let's configure this if we want to add an intermediate bus converter, which in most cases you will want to do that, and it will open those dialog settings for the IBC. At this time, we also have an option if we want to configure a power interface module. For this example, let's do that. So we'll configure a PIM. Now you see at the top, we are working with PIMs. Presently, there are 8 products that you can choose from, and there's a download of these. You can also filter them to reduce the number of options, but also reduce what you're looking for out of the module. You can select by product type, either digital or analog, mounting type, either through-hole, surface mount, or SIP, and you can also filter based on dimensional criteria, based on the maximum allowable length, width, and height. And you can do this for every single rail grouping that you choose, the product that you select. At this point, we want to go back and select every load in the Xilinx load groupings that we have not selected at this time. Once we have selected all these load groups, we now see they are all present to be configured, as well as the IBC and the PIM. Now it is time to run optimization. And again, we are running the optimization to maximize the efficiency for now. Okay, we notice at this point several things. Note that all devices have been chosen and automatically selected by the optimization tool. We also notice the total system efficiency located in the configuration browser under efficiency is 82.17%. Also notice that a 1/8 brick with a bus voltage of 4.72 volts has been selected to have the optimum efficiency or the highest efficiency for this solution. So this 4.72 volt intermediate bus rail will be driving all point of loads. And speaking of point of loads, we see that the high current rail, which is roughly 65 amps, is presently configured with 3 point of loads in parallel. Now let's move the slider all the way to the left and run the optimization again. This time we're running it more for a closer match of the total power that is needed. Now we see a couple of things. First of all, we see the total efficiency has dropped about 4.5% from around 82.2% down to 77.5%. We also see that now we have a 16th brick instead of an 8th brick as the intermediate bus converter, and it has been selected to have a 12 volt rail for all point of loads. Also, we have a single point of load now instead of 3. And also just wanted to point out, notice the output voltage of this point of load rather, is 0.92 volts. Now, I'd like to show you another set of tools that's pretty powerful. If you go to the top of the screen, you see the display value output voltage. What this does is show you the output voltage for each module. Now, if we can also now change that to efficiency if we would like. Now it's 89% for this one, 95% for this load. But let's go back to the output voltage. And I want to show you the effect of going from 1 milliohm to just 2 milliohms a PCB resistance, and let's run the optimization again. Notice the efficiency is presently at 77.5%. So let's see how much difference the 1 milliohm makes to the entire solution. We see it's dropped over 3%. So I point this out that for instance, when you have high current loads, obviously it's important to design with an optimum low PCB resistance, but this really demonstrates the effects that this can have on your overall system efficiency. So I'll put this back to the 1 milliohm for now. I also wanted to point out that you're not limited to using Flex power modules for your product selections. The Flex power module Power Designer permits the inclusion of non-Flex products. And here's an example. Let's go down to the bottom of the Xilinx power tree. Let's select this last load. It's basically a 1 watt load. What we can do is hover the cursor over this black dot, and we see the black dot is now turned blue. We right click and we create and connect a point of load. Now, rather than go through this entire list of parts to make it easy, we're looking for a generic point of load. So we'll start typing generic, and we see 3 generic devices. First, is a generic point of load. We have a generic PM bus device, should you want to choose one of those, and also a generic IBC. Also, in the near future, there will be a 4th generic product added to this selection, the generic LDO. But in this instance, we want to go ahead and select the generic point of load. So we left click on that, and we can scroll down to this rail, and we can see that it has replaced the Flex part in this rail. Also wanted to point out, you can find this part over in the configuration browser. Under loads, we see the generic point of load. We can click on the rail number and see that presently this generic part is a 1.8 volt part, and the default is 90%. Well, your efficiency probably won't be 90% for 1 watt. Let's say 80%. And when we enter 80%, notice the power dissipation automatically changes. So go back to the system view. Now, while today's demonstration is focused on the new updates to the 4.0.1 release of the Flex Power Designer, I want to mention that you can also add non-Xilinx loads and power rails to your power configuration and use a system optimization tool with those loads, just as we've done with a Xilinx product. The Flex Power Designer can also perform loop optimization and fine-tune output transients to meet load requirements. Due to time constraints, I will not go into the operation of these functions, but I wanted to let you know that these tools are in the Power Designer.
Thanks, Bob, for the presentation. To download your free copy, please head to flexpowerdesigner.com, where you can get started straight away without any hardware requirements. For additional support wherever you are globally, you can also contact us via email at pm.support@flex.com. Thank you.